Hello and welcome to Learning with Lovo. This is part 3 in my helicopter deep dive and the last half of helicopter aerodynamics. Let's get back into it. Induced drag, parasite drag, profile drag. As with most vehicles, the power versus drag interaction dictates a lot around what a helicopter can do. We have 4 areas to consider at any given speed: rotor drag, induced drag, parasite drag, and power available. Rotor drag. The rotors require power to turn and create drag by turning. For a conventional rotor system, forward speed adds more drag on the advancing blade and a little less on the retreating blade. This means more power is needed the faster you go. However, at first this is slightly balanced out by the airflow over the tail rotor, making it more efficient, giving you a power to speed curve like this. Induced drag. You're going to need thrust to move, and increased thrust means applying collective. This increases blade pitch and creates more drag. This induces airflow down through the disc, and the power needed to maintain rotor RPM is the induced power. When moving slowly, your rotors will be in the induced flow. As we saw when discussing translift, this means the advancing blade will experience forward airflow and downward airflow. The overall airflow is diagonally down, which reduces the AOA of the blade. The more induced flow, the more blade pitch you need to give the same AOA. As you increase in speed, you will outrun the induced flow, and the airflow will move more to be from the front. This means less AOA required, which means less blade pitch and less drag, giving you a power to speed curve like this. The dotted line on the left shows the curve if you aren't in ground effect. Parasite drag. This is the drag from the airflow over the airframe. The faster you go, the more there is, and it's an exponential increase, giving a power speed curve like this. Power required curve. We can combine these curves to give us the required power to fly at any given speed. Power available. The power the engine can output is fairly constant and varies depending on the weather, weight, and altitude. The areas of the power required curve underneath the power available line show air speeds the helicopter is capable of. If we're really high and heavy, we might not be able to hover at all. The more space between the two lines, the more excess power available, and therefore the more the aircraft can maneuver or climb. The chart can give us some useful numbers. The point with the greatest excess power tells us the ideal endurance speed for time and level flight, and the ideal climb speed. Where the curve meets the power available line, we have our maximum level flight speed. Where a tangent from the origin meets the curve, or the shallowest part of the upward curve, we have the best endurance speed for range, as this shows the best increase for speed for the least increase in power needed. This is why helicopter pilots perform power checks. This means hovering and seeing how much power that takes. From this data and consulting aircraft-specific charts, they can figure out what the helicopter can do in those conditions. Windvane. The airflow from any direction will create a force on the parts of the aircraft it hits. If you're flying canted to one side, the side shielded from the wind won't have a significant force, and we have a tail sticking out way at the back, giving a large turning moment, so the aircraft will want to turn. This will occur until you overturn slightly, pushing you the other way until you settle out facing the wind. You could oppose this with yaw pedals if you wanted for a braking effect, but the main feature of this is that the faster you go, the more the aircraft will want to stay pointed into the airflow. In addition to this, a gust of wind from the side will interact with the tail rotor in the same way induced flow interacts with the main rotor. If your tail rotor is on the right, a gust of wind from the right will reduce its AOA, which reduces its thrust, which will also swing the airframe right. In a hover, you may find yourself yawing back and forward as the tail rotor oscillates in thrust with no change in pedal input. In forward flight, inertia and the wind vane effect will largely keep you on track. So if you haven't balanced the main rotor torque with the right amount of yaw pedal, you won't spin around, however you will tend to oscillate a little. Anti-torque. Let's talk about the tail rotor a bit more. We know there is a torque on the main rotor, so there is an equal and opposite torque on the airframe. If the torque reaction is too little, the airframe will turn in the opposite direction of the rotor. This is opposed by a tail rotor in a traditional aircraft, or another lifting rotor turning in the opposite direction in a coaxial tandem or intermeshing or transverse airframe. The tail rotor is linked to the main gearbox and therefore responds to engine RPM changes in the same way the main rotor does, though in a greater gear ratio. Should the torque from the main rotor match the anti-torque effect of the tail rotor, you will maintain a constant head-in. If not, or by use of pedals to change the pitch of the tail rotor blades and therefore the anti-torque thrust, you will turn about the rotor shaft. Note, this will affect the load on the engine in a similar but smaller way to increasing the collective pitch on the main rotor. Also, sideways thrust will apply a sideways drift to the craft. Sometimes you have to apply an amount of side stick to counter this. Some helicopters actually slant the main rotor drive shaft to offset this. Loss of anti-torque. As you can imagine, losing the tail rotor can be quite bad. This will most likely happen in DCS due to taking damage from enemy fire or from you hitting something with it. You will immediately lose the anti-torque effect and so will experience a yaw as well as dead pedals. What should you do? If in forward flight you have a few options. The yaw is proportional to the main rotor torque, so shutting down the engine and auto-rotating to an engine out landing is a good bet. More on auto-rotating later. Option 2 is to engine on auto-rotate to about 70 knots and apply power until just before the yaw effect gets too much. Fly at an angle if you need to. Now you're basically Zoolander and you can only turn in the direction your yaw wants to take you. Fly this way to a suitable landing spot and perform a spiraling approach to a fast landing. If you're in a hover, this is pretty much a guaranteed bad time. You'll have no Windvane effect and a lot of torque being used to maintain the hover. The safest thing to do is to immediately shut down the engine and auto-rotate to an engine off landing. Additionally, you can lose the tail rotor without losing the tail rotor. Certain aerodynamic situations can lead to loss of tail rotor effectiveness, or LTE. This can only really happen below about 40 knots and will result in an uncommanded yaw that can get really bad. This can happen if 1. A high wind coming in from the front quarter of your advancing blades can blow blade tip vortices over the tail rotor, reducing its effectiveness. 2. If you're flying with a strong enough tailwind, this should always be avoided, a strong reverse weathervane effect can occur. 3. Similarly, a strong enough wind from the front quarter can windvane with more force than your tail rotor can fight. A crosswind coming in from the side that your tail rotor is on can result in the tail rotor going into Vortex ring state. 5. There are more, but I don't want to spend too long on this topic. What should you do? The common theme for resolving rotary wing issues is to be high and get forward speed. This is no exception, as you should look to maintain full yaw opposing pedal, increase forward airspeed, and if height above the ground allows, lower the collective. Vortex ring state. The dreaded vortex ring state. You'll be flying slowly along in a descent and before you know it, you're dropping out of the sky. Let's see what it is and what we can do. A vortex is a swirl of, in this case, air. They come off the ends of wings, rotor blades, propellers, and anything else moving quickly enough through a fluid. In certain circumstances, the vortices will roll back into the rotor disc strongly enough to cause the blades to stall and you to drop out of the air. There are 3 things we need to get into VRS. 1. We have induced flow passing down through the rotors. 2. We have external airflow directly opposing the induced flow. And 3. The forward airspeed is low. So we can see a slow speed descent is a real danger zone for VRS. We should also watch out for pulling big flares like a quick stop, downwind approaches, why are you doing this, and steep approaches. If we consider the hover, the rotor movement and induced flow gives you the AOA of the blades. This will increase at the root as the blades twist more there. The rotor tips always create vortices, and as we're hovering, we're not moving forward and away from them. They will increase the induced flow. When you lower the collective to descend slowly, there will be a downwards induced airflow from the rotor and vortices, and an upwards flow from the rate of descent. The blade tips will have a lower AOA than the root because while the vortices build and balance out the increased rate of descent flow, the lowered collective means you have tilted the blade into the relative flow. The blade root, however, does not have significant vortices, so the induced airflow begins to balance out with the descent flow, increasing the AOA here. So the tips have low AOA but are moving quickly. The roots have a high AOA and are moving more slowly. If you lower the collective further and we begin to descend faster than is safe, the effect increases until the blade's root AOA gets too high and that part of the blade stalls. While the blade root is stalling, the blade tip has a very little lift as the lowered collective and increased descent has killed the AOA even more. There is now only the middle section of the blade providing good lift, and you are descending faster and faster. Vortices increase and interact with the blades, making it move erratically. If you get past a certain rate of descent, raising the collective will only churn up the air more, making it worse. What can you do? Firstly, avoid VRS. Take great care when performing hovers or slow, steep or downwind approaches. Don't do downwind approaches. Also, bear in mind that a large flare, such as in a quick stop, can mirror a descent, as you are tilting the rotor disc back such that the horizontal airflow comes in more from the bottom. VRS recovery. You can get out of VRS by increasing airspeed by a large nose down attitude change, then applying power. If sufficient height is available, entering auto-rotation by reducing power to 0, then gaining airspeed. However, it may be very difficult to prevent the rotor overspeeding. Or the Voigtchard recovery, a technique developed by Claude Voigtchard. Here we would apply power pedal and opposite cyclic, then collective to counter the pedal input. The effect of this should be to slide us to one side, and eventually our advancing blades will hit the upwards part of the vortex. At this point we disrupt the vortex and get our lift back. I highly recommend watching Claude's video performing this with water spraying into the air to show the vortex. Retreating blade stall and compressibility. As well as cyclic control limits, available power and structural strength, a main factor that dictates the max forward speed of a helicopter is retreating blade stall and compressibility. The retreating blade's airspeed is its rotation speed minus the aircraft's forward airspeed. The rotation speed will increase from quite low at the root to higher at the tip. However, the reduction from forward airspeed is the same all the way across. Should you go faster than the root is spinning, you will reverse the airflow there and lose the thrust from that section. You can increase the cyclic pitch to make the breast of the blade work harder and the aircraft go faster, spreading the effect up the blade as you accelerate. Eventually, the cyclic you continue to pull to go faster will cause the whole blade to stall. This will cause you to pitch up and roll to the retreating blade side. A small onset of this can cause you to automatically flare and slow. A large onset of this can cause a loss of control. You can also get this effect from high G maneuvers, excessive control inputs, and flying in turbulent air. For compressibility, if the speed of the rotation of the advancing tip of a rotor blade plus forward airspeed begins to approach the sound barrier, we get more and more compressed air in front of it. You can expect a performance decrease as the drag ratio shoots up, as well as vibration and noise. Some aircraft use modified blade tips to deal with this better at the loss of low speed performance. Auto-rotation. You've no doubt heard about auto-rotations as an emergency maneuver, and it's definitely something you should practice. Let's take a look at what it is and what to do. Normally, rotor drag is overcome with engine power. Should the engine fail, we need something else to keep our blades spinning. We can use the air we're falling through to push the rotor around, and this is what an auto-rotation is. As rotor blades are made twisted, with more angle at the base where it's slowest and less at the tip where it's moving fastest, as we descend without power, the higher angled inner section will be pushed a lot by the upward flow as the helicopter descends. This airflow is called the autorotative force. The lower angle section at the tips will be spinning faster, providing lift as well as rotor drag. To keep a constant rotor RPM, we need to be descending fast enough that the autorotative section can deal with the rotor drag, plus the drag from all the other stuff like tail rotors. Should you pull collective here, you will get more lift, but you will stall some of the autorotative section and increase drag. This will quickly reduce your rotor RPM. You effectively have energy you can put into the rotor by descending. You can use that energy for lift and control, but that both uses up the energy and reduces it replenishing. If you're hovering, your engine dies and you dump the collective, it'll accelerate straight down until the rotor RPM balances out and you continue at that rate of descent. If this happens during forward flight, the rate of descent will start, but where it balances depends on how fast you're going. What do? Try not to panic. Dump the collective, If you're hovering at low speed, try and get faster by pushing the stick forward. This may need a little collective to work. If you're fast, you may need to flare a little. You're now looking for a landing spot. You can trade rotor speed for maneuvers, but you'll have to get it back again after by descending more. You're going to do an auto-rotative landing. This means continuing like this until you're close to the ground, where you trade most or all of your remaining rotor speed for lift in a flare and likely a running landing. Perform this too soon and you'll drop the remaining height. Too late and you'll hit the ground too hard and fast. I recommend trying a few by cutting the engine in DCS from various setups. You can trade rotor speed for maneuvers, but you'll have to get it back again after by reducing collective and either flaring or turning. This will bring more airflow from the bottom of the disc, feeding the auto-rotative section, as well as flapping up the disc and allowing conservation of momentum to build the rotor speed. Just like an ice skater pulling their arms in close to their body to spin faster. Avoid areas. Your best bet for not dying in an auto-rotative attempt is to adhere to the avoid areas. This is a speed height graph that looks something like this. The shaded areas represent altitudes and airspeeds that make it very difficult to auto-rotate. As you can see, flying slow or hovering at higher altitudes than you could fall without exploding is death, until you get high enough that you have time to gain forward airspeed. Here you'd survive the drop, here you wouldn't, and couldn't get the airspeed you need. Here you could. Similarly, flying fast would cause a large descent rate if auto-rotation set in, so flying lower and fast could lead to a sudden slamming into the ground, should the engine or drivetrain give away. Sticking to the clear sections is the best way of being prepared for an auto-rotation. That's it for part 3 of my Helo deep dive. Watch out for my next episode coming soon. The following 2 videos will be on flight techniques. Thanks for watching, Learning with Lovo. Okay, here we are flying along just nicely in this Huey. Here comes this rotation there, done the collective. Now we need to get the flare on to maintain the rotor RPM's coming up. That's good, speed about there, hold that descent. Close to the ground, so we have to put the power on and flare, power on and flare, power on and flare, power on and flare, don't hit the tail, and skid landing.